Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry Paper 3. In the Unit 4, Heterocycles Part 2, we will be studying about Pyrazoles Synthesis reactions and uses as the first lecture. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be covered in this session include synthesis of pyrazoles, from 1,3-dicarbonyl compounds and hydrogen, how pyrazoles can be synthesized by ring transformation reactions, 1,3-dipolar cycloaddition reactions, multi-component coupling reactions are some of the reactions we will be studying for the synthesis of pyrazoles. Afterwards, we will be studying about reactions of pyrazoles. We will be mainly focusing on electrophilic aromatic substitution reactions and N versus C metallation reactions. And finally, we will be studying about uses of various pyrazole derivatives. Let us look at heterocycles 2, part 2. So, in this session, we will be studying about 5-membered heterocycles with 2 nitrogen atoms. And there are some names of the heterocycles are given here: pyrazole, isoxazole, isothiazole, imidazole, oxazole, and thiazole. Pyrazole and imidazole are the 2 nitrogen heteroatoms. Isoxazole and oxazole are the 5-membered heterocycles having nitrogen and oxygen as the heteroatom. Isothiazole and thiazole are the 2 compounds with nitrogen and sulfur. So, in this particular case, pyrazole, isoxazole and isothiazole are called as 1,2 azoles. That means the substitution is 1,2 positions. And imidazole, oxazole and thiazole are called as 1,3 azoles. Here the position is the nitrogen with the hydrogen is considered as number 1. So 1, 2, 3. So these are 1,3 azole, that is 1,3 substitution in the 5-membered heterocycle. So these are all the major classifications by which these 6 compounds are categorized. And in this particular session, we will be focusing on the studies of pyrazole, that is their synthesis, reactivity, and some of its biological applications. So what is a pyrazole? Pyrazole is nothing but a 5-membered heterocycle with 2 nitrogen atoms, and as we had seen, this belongs to 1,2 azole family. That means nitrogen, both the nitrogens are in position 1 and 2. And it is actually sp2 hybridized and delocalized 6pi electrons heteroaromatic ring system with 2 adjacent nitrogen atoms. That is the lone pair of electrons on this nitrogen is also involved in the 6pi electron aromatic pi bond formation. And of these 2 nitrogen, the nitrogen which is hash is the lone pair for it is the non-basic one. This nitrogen with the hydrogen is the one which is a non-basic one, because this gives or donates this 2 lone pair of electrons to the aromatic pi bonding, and the other nitrogen does not share its lone pair. So this is the basic nitrogen, and this is very similar to normal amines. And the various resonance forms are shown here. In the case how the pyrazole can exist as various resonance forms. So here are the 1, 2 and 3. All the carbon atoms can have the negative charge, and in this particular case nitrogen can also have a negative charge. So these are all the various resonance forms which can exist for this particular pyrazole moiety. And when we talk about reaction, this will be very crucial in understanding how the pyrazoles undergo reactions. Some of the important Parasol drugs are shown here. Viagra is a very famous blockbuster drug, and sildenafil is the actual name for this compound. It is used for erectile dysfunction and pulmonary arterial hypertension. This compound has this unit is the Parasol unit that is present in this particular drug, and celecoxib or Celebrex is a COX-2 inhibitor, and it's a non-steroidal anti-inflammatory drug. This drug has again Parasol moiety that is present, and sulfafenazole is an antibacterial drug, and ruxactinib is another anti-tumor reagent. So both of these contain the Parasol moiety. And let us look at the various synthesis of Parasols. We have various reactions which leads to the formation of Parasol. Some of them are listed here. The Parasol can be synthesized from 1,3-dicarbonyl compounds and hydrazine. This can also be synthesized from alpha enones and alpha inones. From alkynes we can synthesize by ring transformation reactions, 1,3-dipolar addition reactions, and multi-component reactions. These are all the various types of reactions by which Parasols can be synthesized. We will be looking at the individual steps one by one. Here are a couple of references which are given here for those who want to know more about these synthesis methods. Before we start into the actual synthesis, let us look at what is the retrosynthetic analysis and how it actually helps in designing many of the synthetic pathways what we are going to see. So what is a retrosynthetic analysis? It is nothing but a backward analysis, or in other words it's a reverse engineering. So the end product or the final target molecule is broken down into pieces. So that is what is basically the main objective of retrosynthetic analysis. So the complex product is broken down into simple starting materials, so which is similar to reverse engineering. And here we need to identify the functional groups, what are all that is undergoing changes, and what are all the different types of bond disconnections that are possible. So these are all the two crucial steps which are essential for designing a retrosynthetic analysis. And this method was pioneered by Professor E.J. Corey. He is Nobel laureate in chemistry in 1990. He received his Nobel Prize. And Parasol is basically 1,3-dicarbonyl plus hydrazine. So this is one of the way how we can actually break this molecule. Say let us look at Parasol molecule. This can undergo tautomerization as shown here, and this compound can be broken down here because we have a double bond here. So this double bond can be broken down, and we can have carbonyl units there. And these two nitrogen can come from hydrazine as shown here. So this is the way we actually break the final molecule into whatever the possible starting materials are. So this is how the retrosynthetic analysis works. In the actual synthesis, we mix these two things to get the final product. In the retrosynthesis, it is actually done in the paper only. This is also called as a paper analysis in the beginning, and from the paper analysis we can actually find out what are all the different bond disconnections. That is what we have written here. So the bond disconnection is, there is a carbon nitrogen double bond. So this bond can be broken down like this carbon can have an oxygen and the nitrogen can come from outside. The same way we have the carbon nitrogen double bond which can be broken down like a carbonyl group on one molecule, and the nitrogen can come from the other side. So this is the way we can actually do a retrosynthetic analysis, and based on that we can also design how the compound can be synthesized. So here again, based on the retrosynthetic analysis, we have identified a diketone can be a starting material. So the same way the actual synthesis is carried out, 1,3-diketones when treated with substituted hydrazines give substituted Parasols. The same way, instead of a ketone, we can also use a ester. So this is nothing but a 1,3-dicarbonyl compound again, but this is a beta ketoester. So this beta ketoester can also be treated with substituted hydrogen to give the hydroxy derivatives of pyrazoles. So we are introducing one additional functionality in this molecule which can be manipulated further. In this one we have a dicarbonyl, but one more ester entire unit is present. So this is again 1,3-diketo, and there is also an ester. This compound can also undergo reaction with hydrazines to give ester derivative of pyrazoles. So this is how we can actually make various functionalized hydrozoles by pyrazoles by taking different starting materials. And if we look at the reaction mechanism for this particular transformation, the carbonyl compound is shown here. This is a 1,3-diketone, and in the presence of an acid, because this reaction is catalyzed by acids, and we can have the second unit can come be as oxygen or nitrogen. If it is nitrogen, then this compound is nothing but the hydrazine, and if it is oxygen, then this is hydroxylamine. So if we replace this X with oxygen, then what we end up is basically isoxazole as shown here. If we have nitrogen here, both are nitrogen, then we end up with the pyrazole. So let us look at the mechanism one by one. This carbonyl carbon is more electron rich, so it abstracts the proton, and this oxonium ion is formed as shown here, and the nitrogen is having a lone pair of electrons, and this carbon, because oxygen is more electronegative, so this will pull the electron towards itself, making this carbon highly electrophilic. Since this carbon becomes electrophilic, the lone pair from the nitrogen actually attacks here, so we end up with this particular intermediate that is formed, and this undergoes proton transfer, and that proton transfer means one of the hydrogen from this nitrogen moves to this oxygen, and during this process what happens is we are having a oxonium ion. So this oxonium ion is a very good leaving group, but in the first case whatever we have the hydroxyl unit, this is not a good leaving group, so this poor leaving group is getting converted to oxonium in this particular case, and this loses water molecule, and there is this proton is also lost, and that leads to the imine formation. So this is very similar to the intermediate which is formed in the enol in the Parasol synthesis, and we have another carbonyl unit. So this can also undergo similar reactions as we have seen here. So it will abstract the proton first, and once it is there, now there is no external nitrogen that is coming and attacking this electrophilic carbon. The internal atom that is having the lone pair of electrons. So if it is pyrazole we want to synthesize, we will be using hydrazine here. So this is the nitrogen. So the lone pair of electrons from the nitrogen attacks this electrophilic carbon, and this is the crucial step which leads to the cyclization. So once the cyclized intermediate is formed, because here the heteroatom is having a positive charge which is quite unstable, so in this particular case the proton transfer actually takes place. This proton is lost from this heteroatom because it is having a positive charge, so the loss of proton makes this heteroatom neutral, and this hydroxyl unit oxygen, which is more electronegative than the nitrogen here, abstracts this particular proton to form hydronium ion as shown here. So this loses water molecule, and here the lone pair is donated from this heteroatom to this particular carbon heteroatom bond, and the loss of proton leads to the final aromatization back to the pyrazole derivative. So finally we end up with the cyclized pyrazole derivative as shown here, and instead of nitrogen, if it is oxygen, then this compound is nothing but the isoxazole. So this is how the entire mechanism actually proceeds. And let us look at the Regio Selectivity in the Parasol formation, because if we are using an unsymmetrical diketones, then there is a possibility that how the reaction actually proceeds. But in this particular case, between R1 and R2, the tautomerization between these two nitrogens are possible. In other words, we will actually end up with the similar Parasol derivative, but the position of the equilibrium basically depends on what is the alkyl group that is present, whether it is highly electron donating or not. Based on that, one of the isomer is formed or one of the isomer is stable. If we have an electron withdrawing group, that is a ester group which is attached to this carbon, then that makes this carbon much more electron deficient. That means when the reaction actually occurs, we will end up with this kind of substituted product. So this is one of the way we can control the regio selectivity of the product formation. So in this particular case, the NME derivative is formed here, and this is 1, 2, 3. So we can get the 3 substituted derivative more effectively because of the presence of this ester group, which is highly electron withdrawing. The same way, if we have aromatic unit, that is the paranitrophenyl unit is present, which is also a very good electron withdrawing group, then again we are going to end up with the 3 substituted derivative where the aryl unit is present. So between 3 and 4 substituted products, we can actually control the regio selectivity by carefully choosing the starting material. The electron withdrawing groups, if they are present on whichever carbonyl, that leads to the 3 substituted Parasol derivative. Another method is Wills-Meyer-Hack protocol. So we can prepare parasols using the stepwise addition reactions of substituted hydrazines to unsaturated ketones, followed by this is the case, and followed by cyclization under Wills-Meyer-Hack conditions. So in this particular case, this is the carbonyl unit, and this is nothing but the Wills-Meyer-Hack reagent. This is nothing but N,N-dimethyl formamide having the acetal unit here. So this undergoes condensation with the carbonyl compound on this particular methylenic carbon. This leads to this particular intermediate. This can on hydrolysis gives this corresponding hydroxy derivative, and this hydroxy derivative reacts with a hydrazine, substituted hydrazine, to give the our final compound, which is the substituted Parasol unit. We can also synthesize parasols from alpha enones or alpha inones. So here we have the ine, that is the alkyne, and the carbonyl, both the units are present. So this is a ketone and this is an alkyne. So alkyne ketones can also be used for the formation of pyrazoles. So this is how the product formation is here. The R3 unit comes from the hydrazine part. So the hydrazine part, this is the part which comes from the hydrazine, which is attached to the nitrogen. And here we have 2 ways by which the actual condensation can take place. So in other words, we are going to get regio isomers in these kind of reactions. So depending on what is the group R1 and R2, we may get different ratios of the final product. The same way, if we use alpha enone, that is alpha beta unsaturated carbonyl compound treated with hydrazines, substituted hydrazines, and this can undergo oxidation to give either this product or that product. That means, in other words, we are going to get regio isomers of these products. So alpha enones and the alpha inones generally give mixture of regio selective products. So depending on the substituents, the product ratio varies. And here is another method from alpha enones. So in this particular case, we have an alpha beta unsaturated system. We can epoxidize the corresponding double bond to give the keto epoxide. So here the treatment with the hydrogen peroxide gives the epoxide. Then this derivative is treated with hydrogen peroxide under reflux conditions. This gives a pyrazolene intermediate, and this on treatment with acetic acid yields the corresponding pyrazole unit, and in this particular case the yield obtained are very high, 70 to 80% we are getting. So in other words, the alpha beta unsaturated compound can be converted to pyrazoles through the process as shown here. Next, let us look at Parasol synthesis from alkynes. So here, the terminal alkenes are reacted with N-alkylated tosyl hydrozones in the presence of Lewis acid AlCl3 to give 135 tri-substituted pyrazoles. So this is the N-alkylated, this is the tosyl part. So this is prepared from, actually aldehyde is the starting material, and aldehyde is treated with hydrazine to form the hydrazone. So tosyl group is present, so it is a tosyl hydrazine is the starting material giving tosyl hydrazone, and the nitrogen is actually having a substitution here. So this is the starting material which is reacted with terminal alkynes in the presence of AlCl3 gives the substituted, because this R group whatever is present on the nitrogen is present here. So RNN, this part comes from the tosyl hydrazone part, and this is our aromatic unit which is shown here. Here we have one aryl unit on the tosyl hydrazine, and there is another aryl unit present on the alkyne. So both are given here as the final product. Here again this is a 3,5 disubstituted hydrazine. So in one position also there is a substitution. Instead of that, we can also get a one position unsubstituted compound, that is a 3,5 disubstituted pyrazole also can be prepared. So in this particular case, the aldehyde is treated with tosyl hydrazine. In this case, this is not N substituted, that is N-alkylated tosyl hydrazine is not used as a starting material. Here this is simple tosyl hydrazine directly. So this tosyl hydrazine directly reacts with an aldehyde to give the same intermediate which is the tosyl hydrazone, and this tosyl hydrazone reacts with the terminal alkene to give the 3,5 disubstituted pyrazole. In this particular case, the nitrogen is not substituted. So this is how in both the cases, the first case we use AlCl3 as the catalyst, and in the second case we are using a very high temperature for this reaction to occur. So these are all the two different ways by which terminal alkyne can be converted to tosyl, converted to pyrazole. We can also form pyrazoles using ring transformation reaction. So here in this case we are starting from the pyranones are treated with aryl hydrazines, and this condensation of 2,3-dihydro-4H pyran 4-one, this is the starting material with aryl hydrazines in ethanol. Ethanol is used as a solvent, and this is a montmorillonite KSF as a catalyst. This at 80 degrees centigrade gives the corresponding 5 substituted pyrazoles. And when we use furan 2,3-diones as shown here, again it is condensed with aryl or alkyl hydrazines. Here the solvent is benzene, and under reflux conditions it gives a pyrazole 3 hydroxides. So these are all the two ways. Here we are using two equivalents of the hydrazine. In this particular case we are using only one equivalent of the hydrazine. So these two other heterocyclic rings are converted to pyrazole rings. The next one is a 1,3-dipolar cycloaddition reaction. So here we are using ethyl diazoacetate as one of the substrate. So the synthesis of pyrazole 5 carboxylates from ethyl diazoacetate and alpha methylene carbonyl compound. So here we have a methylene group, and this is a carbonyl compound. In the presence of a base, DBU is used as a base, gives two regio isomeric products. In both the cases we have a 5 position, that is if we go from 1, 2, 3, 4, 5. So 5 substituted carboxylate products are formed. The only thing is these two are giving the regio isomers between 1 and this is 1, 2, 3. So 3, 4 disubstituted regio isomers are formed. And when we use alkynes with ethyl diazoacetate in the presence of triethylamine as the base and zinc triflate as a catalyst, it gives the pyrazole derivatives. So in the case of multi-component coupling reactions, the diazo compounds prepared in situ. So here we are not preparing the diazo compound. This is the diazo derivative which is not prepared or added directly, but it is prepared in situ from the tosyl hydrozones which is formed. So as usual, the formation of tosyl hydrazone is very simple. The aldehyde is treated with tosyl hydrazine, that gives the tosyl hydrazone. This hydrogen is abstracted by the base to give the corresponding diazo derivative, and like the previous one, the diazo derivative is treated with alkyne to give the substituted pyrazoles. And in another case, we can also form the in situ formation of the hydrazone. The reaction is shown here. We have a diethyl oxalate as one of the reacting material, and the cyclization of this diethyl oxalate with dianion of the hydrazone. This is the hydrazone. The dianion dianion is generated by the use of butyl lithium as a strong base. So use of butyl lithium as a strong base gives the dianion that reacts with the dicarbonyl compound to give the corresponding parasol derivative. The next one is a NOR synthesis. So in this particular case, the parasol derivatives are prepared from 1,3 dicarbonyl compounds and hydrazines. So here again we have the regio isomers are possible. Two regio isomers are the different derivatives parasols are formed in this particular reaction. Depending on the substituents that is present in the dicarbonyl compound, and this nitrogen substitution remains the same for both the cases because NR4 remains the same because this unit comes actually from the hydrazine unit. So this remains the same, but only changes the carbonyl compound can, depending on the electron withdrawing nature of the groups, the different products can be formed. If you look at the reaction mechanism, the first step is the terminal amine from the tosyl hydrazine attacks the electrophilic carbon, and this leads to the imine formation. So here again the carbonyl, this amine can attack either the carbon which is attached to R1 or the carbonyl carbon which is attached to R3. So these two positions can be attacked by the corresponding hydrazine. So in this particular case, we are only showing from the R1 side attack. So that is the reason this step may lead to isomer formation, which is the starting step and which leads to finally the product which is having regio isomers. So once the initial imine is formed, so this is the imine that is formed after the loss of water molecule, and this imine, the nitrogen having lone pair, can internally attack the carbonyl electrophilic carbonyl carbon. That leads to the cyclization. So this is the crucial step for the ring formation reaction, and this leads to the diimine product, and this can undergo loss of water molecule to give the parasol derivative as shown here. So the simplest steps are, we have two nitrogens and we have two carbonyls. So one of the nitrogen attacks the carbonyl and the second nitrogen attacks the other carbonyl, and we get the cyclized product. So this is how very simply we can understand the whole process. Of course, there are two water molecules that are lost in this reaction because there are two oxygens are present in the starting material which are not present in the final product. So these oxygens are removed as water molecules. Let us look at Parasol reactivity. So the pi electron densities are shown here. This NH nitrogen is having the highest electron density at 1.649, and the C5 is having the least electron density at 0.957. and the third carbon is also having a low electron density at 0.972. Another nitrogen is having an electron density of 1.278, and the carbon 4 is having electron density around 1.105. So we have the N1, that is a pyrrole-like nitrogen, and there is another nitrogen which is a pyridine-like nitrogen. So that means the lone pair of electron is available on this nitrogen alone, and in the case of pyrrole-like nitrogen, the lone pair of electron is involved in the pi sextet formation. The 6 pi electrons are formed with the help of a lone pair from the NH electron. So that is the reason this nitrogen is called a pyrrole-like nitrogen, whereas this another second nitrogen is a pyridine-like nitrogen. So this is basic compared to this nitrogen. So because of the presence of both electron withdrawing nitrogens, the electronegativity of the nitrogen is more than the electronegativity of carbon, and the nitrogen pulls the electron towards itself. So making these two carbons, that is C3 and C5, less electron density. So that is the reason here it is shown like there is a reduction of electron density on C3 and C5, whereas this carbon, the carbon number 4, which is away from these two nitrogen, is relatively retaining its electron density. So in the presence of a strong acid, the protonation of the pyrrole takes place, and it gives a pyrazolium cation, which can undergo preferential electrophilic substitution at C3 rather than C4. So this is how actually the reactions happen in the case of pyrrole. So this is a more electron rich carbon. So this carbon can undergo electrophilic attack. These two carbons, C3 and C5, are electron deficient. So the nucleophile can attack these two carbons. So the Parasol anion is reactive towards electrophiles. So this is how the nitrogen and the carbons undergo reactions in Parasol. And let us continue with Parasol's reactivity. So the Parasol ring is actually resistant to oxidation and reduction, but the groups such as alkyl and formyl attached to the ring are oxidized to the respective acids. So that means an aldehyde group that is present or an alkyl group that is present in the Parasol can be oxidized to the corresponding carboxylic acid. And on electrolytic oxidation, ozonolysis and a strong base cause ring opening. So this is how we can actually break the Parasol ring by ozonolysis or using a strong base. And we have seen two different types of nitrogen that are present here. So this is the NH nitrogen. So the one of the electrons are shown here in the p orbital. So we have 2 electrons from this nitrogen is involved, and 1, 2, 3, 4 and 5 and 6, 2 electrons here. So there are 2 electrons from here and 4 electrons from the other elements, forms 6 pi electron for this pi system, and this nitrogen is having 2 electrons in the sp2 hybridized orbital. This orbital is actually perpendicular to the pi plane. So in other words, the electrons, the lone pair of electrons present on this nitrogen, which we call as a pyridine-like nitrogen, has lone pair which is perpendicular to the pi systems. Due to that, these 2 electrons are not involved in the pi bond formation, and that is the reason this electron is available, and this nitrogen is basic because of the lone pair which is present in the sp2 orbitals, which is perpendicular to the pi plane. And when we look at acidity and basicity, so imidazole and parasols are shown here. Pyridine is also shown here. So the imidazole is having a pKa of 14.5 and the Parasol is having a pKa of 14.2. So they have an acidic proton on the nitrogen. So in other words, they have comparable acidity of this hydrogen. But the lone pair electrons available on the pyridine type nitrogen is not involved in the aromaticity. That's what we say. Those electrons are in the sp2 hybridized orbital, which is perpendicular to the pi plane, and this is available for the protonation. So those two pi electrons behave differently. And this pyridine's nitrogen basicity actually differs. In the case of imidazole, the pKa is 7, whereas in the case of pyrazole, the pKa is only 2.5. So in other words, we can say like the basicity of the nitrogen varies differently, because if you look at pyridine, the pyridine's pKa is only 5.2. So that way we can actually say the pyridine like nitrogen's basicity differs between imidazole and pyrazole. And we can look at inductive and mesomeric effect in Parasol. So as we have seen, Parasol is a weaker base than pyrrole or pyridine. Why? What is the reason for that? The reason is the inductive effect of or the base weakening effect predominates over the mesomeric effect, because inductive effect is through bond electron pulling, whereas mesomeric effect is actual transfer of electrons. So in this particular case, if you look at the Parasol moiety, so there is a inductive effect operating as shown here. So there is a inductive electron withdrawal that is operating here, and this destabilizes the cation. That means we have a Parasol. When a protonation occurs, the protonation is actually happening on the pyridine nitrogen. So when the protonation happens on the pyridine nitrogen, this nitrogen becomes N plus, and but unfortunately neighboring nitrogen pulls the electron towards itself. So inductively it is pulling the electron towards this nitrogen. So this is a quite unstable cation, and that is the reason this is quite unstable. Whereas if you look at the mesomeric electron release in the same case, this actually stabilizes the cation, but unfortunately this effect is very weak compared to this inductive effect. That is the reason the Parasol is a weaker base compared to pyrrole or pyridine, because pyrrole or pyridine we have only one nitrogen, we don't have two nitrogen as in the case of Parasols. And if you look at the relative reactivities, see the introduction of the pyridine like nitrogen as shown here into the 5-membered pi heterocycle causes withdrawal of electron from the ring carbons. So this is one of the reasons, because the nitrogen is electronegative than carbon, so it pulls the electron towards itself. In other words, it actually reduces the electron density that is present here. So this makes azoles less susceptible towards electrophilic attack, because already electrons are removed by this nitrogen, so this becomes electron deficient. So another electron deficient electrophile cannot attack the Parasol very readily. So that is the reason the electrophilic reactions of Parasols are comparatively less compared to pyrrole moiety. And the azoles we can say is much less reactive than the pyrrole, furan or thiophene, because in those cases they are highly reactive towards electrophiles, whereas Parasol is less reactive. But Parasol is somewhat more reactive than benzene itself. So if we compare these three compounds electrophilic reactivity, benzene is least reactive, followed by Parasol, then pyrrole is highly reactive towards electrophiles. Now let us look at the various ways by which the electrophile can attack the Parasol ring. So we have the electrophilic attack taking place on C3, C4 or C5. When the attack takes place on C3 carbon, so this is what is the intermediate formed, and this there is a positive charge on the nitrogen, and this is quite unstable species. That is the reason this is an unfavored one. In other words, what we can say is this attack on C3 is least likely. Whereas if the attack takes place on C4, then we have two resonance structures possible for this intermediate, and when the attack takes place on C5, then we have one structure which is again unfavored, like the attack which happens on C3. So C3 and C5 have one particular structure where the nitrogen is having the plus charge is quite unstable, and that is the reason the reaction at C3 and C5, that is the electrophilic attack at C3 and C5, are not favored, whereas no such destabilizing cation exists in the case of C4 attack. So this reaction is occurring more preferentially for pyrazole moiety. And if we look at the actual reaction itself, the electrophilic aromatic substitution, which is an electrophilic attack reaction. So we have earlier seen pyrrole is more reactive and pyrazole is more reactive than benzene. In this particular case, we will be looking at the pyrazoles derivatives. So the bromination leads to 4-bromo substitution. The same way nitration or sulfonation, all this reaction leads to 4 substitution, because C4 electrophilic attack is more favored compared to C3 or C5. That's what we had seen, and in the reactions also that is actually seen. And let us look at N versus carbon metallation. That is, the electrophile can attack on nitrogen or carbon. So in the unsubstituted pyrazoles, the NH proton is metallated very easily using a strong base like butyl lithium. So in this particular case, this proton, this is the most acidic proton, and this is abstracted. That is the reason the alkylation, that is the electrophilic attack, can take place on this particular nitrogen. So this leads to N-alkylated product. Whereas when the nitrogen is having an alkyl group as shown here in the methyl group, so there is no acidic proton on the nitrogen, so only the carbon can be having an acidic proton. So the butyl lithium abstracts this particular proton, and then reaction with an aldehyde produces the corresponding product as shown here. So the electrophilic attack can take place on the carbon. So depending on whether the nitrogen has the proton, that is acidic proton is present or not, the N alkylations or the N electrophilic attack versus C electrophilic attack can be controlled. Let us look at some of the pharmacological activities of various pyrazole derivatives. We will look at antibacterial, anti-cancer, anti-inflammatory, anti-tubercular, antiviral, anti-Alzheimer's and anti-diabetic activities and anti-malarial activities of various pyrazole derivatives. So in the case of antibacterial and antifungal activity, the compound 1 as shown here, which is pyrazole 3-carboxylic acid derivative, this shows antibacterial activity against Bacillus Staphylococcus, E. coli and Pseudomonas species, and the compound which is 3,4-dicarboxylic acid as shown here in 2A and 2B. So we have the carboxylic acid derivatives which are present in 3 and 4 positions. So these are all the dicarboxylic acid derivatives. They show inhibitory effect on candidata species. Various candidata strains are acted against by this antifungal activity of these kind of compounds. And when we look at the anti-cancer activity, so the pyrazole oxentol derivative as shown here has some cytotoxicity, and it had inhibited tubulin assembly. So this compound, and when we look at the compound 2, there is another compound. This is active against A549 cell line and NCI H1299 cell lines. This is again shown very high anti-cancer activity. And compound 3, that is 3,5-diaryl pyrazole derivative. It shows anti-cancer activity against 5 different cell lines, that is breast cancer, prostate cancer, promyelotic leukemia, lung cancer and colon cancer. So based on different cell lines, these compound shows very high anti-cancer activity. And we have another two more different derivatives. So here this acts selectively on the COX-2 inhibitors, that is anti-inflammatory and anti-analgesic activity is shown by these compounds. And there is compound 2 as shown here. This is a 1H pyrazolyl derivative. This is showing a very high anti-inflammatory activity compared to that of indomethacin, which is a standard drug which is employed. And it also shows a very good selective inhibitory activity against COX-2 enzymes. And when we look at anti-tubercular activity, the compound that Parasol derivative as shown here, one was found to be an active inhibitor of Mycobacterium tuberculosis, and the compound 2 also is a very good active agent against tuberculosis, Mycobacterium tuberculosis, and several INH resistant strains can be inhibited by this particular compound. And similarly, antiviral activities are shown by compound 1. So this pyrazofuran, this is a furan derivative, this is a pyrazole unit. So this pyrazofurin derivative proved against respiratory virus, especially in the HeLa cells, and vaccinia virus, and vesicular stomatitis virus, and influenza A virus. So all these viruses are acted against by this particular Parasol derivative. And this phenyl substituted 1H parasol 3 carboxylic acid was effective against IN inhibition and HAB replication. So these are some of the compounds which are active against viral activities. And there is another compound which is shown here. This is a novel Parasol derivative, and this shows excellent antiviral activity against WTK103N and Y18C mutants, and it also exhibited excellent activity in the cell-based assay for various anti-cancer compounds. Then this 3,5-diaryl Parasol derivative showed the ability to inhibit monoamine oxidase A and monoamine oxidase B. So this is active against these two enzymes, and this compound is highly active against hypoglycemic agents. So these are some of the Parasol derivatives which act like anti-Alzheimer's or anti-diabetic activity. And in the case of anti-malarial and anti-Parkinson activity, the first compound shows very high activity against CQS and CQR Plasmodium falciparum cultures. And the 3,4-D pyrimidine derivative as shown here is a novel modulator of the metabarotropic glutamate receptor subtype positive allosteric modulator. So these are its anti-Parkinson activity is highly established. Then in the case of agrochemical activities, some of the compounds shown here are very active against and they behave like a herbicide, insecticide, fungicide or acaricides. So cyanopyraphen, which has a Parasol moiety as shown here, and fenpyromiate and cyantraniliprole. These are all the different compounds which are used in the agrochemical industry as herbicides, insecticides. In summary, let us recap what we have studied so far. We have studied about various synthetic methods of parasols, from 1,3-dicarbonyl compounds and hydrazines, how they can be converted to parasols, from alpha enones and alpha inones, how parasols can be synthesized, by ring transformation reactions, 1,3-dipolar cycloaddition reactions, multi-component coupling reactions, or some other reactions by which parasols can be synthesized. This also we had seen. In the reaction part, we have studied about the electrophilic aromatic substitution and N versus C metallation of Parasol derivatives. Then finally, we have also studied about uses of various Parasol derivatives. Finally, we have also studied about various uses of Parasol derivatives. With that, we conclude this session. Thank you.